Can it be a one-step thing?
Yeah, we should be able to get now to our final product in one step. So when the base takes this proton, that frees up these electrons. However, we need to make room for these electrons by pushing these. I decided to put on more carbons here, but anyway, that would give us this. And you're remembering, what's the name of this compound?
I don't know, isn't the enolate ion the one that's later gonna?
Right, so this is an enol.
Yeah, yeah.
I think we briefly talked about enols last term. This is an enol. Why is it called an enol?
Because it's...
Oh, it de-somethings and then the double bond automatically moves to O.
Let's see.
Tautomerization.
Yeah, there you go. So that's right. So this reaction right here was tautomerization. This is tautomerization. I think last term we saw that that if you have an enol, it can turn into a aldehyde or a ketone.
Isn't that tautomerization?
Well, either way, it's tautomerization.
Oh.
That's an equilibrium reaction.
Isn't that one preferred, the carbonyl carbon?
That's true. Last term we talked about, I think you guys are remembering, last term we talked about that if you have an enol, you should think of it turning into an aldehyde or a ketone. But actually it's an equilibrium. It's an equilibrium reaction, it's just that the equilibrium favors the aldehyde or the ketone. But it's really going both ways. Last time we talked about producing aldehydes and ketones out of enols. What we just did is we went through the mechanism of producing an enol out of an aldehyde or a ketone. Now, what I was wondering though is why is this called an enol? Well, it's because it's got the alkene and the alcohol. So this is a very logical name because there's the alkene and the alcohol off the same carbon here. So it's logical that this is an enol. An enolate would be a
O minus.
Yeah, that's right. It would be a enol with a negative charge. These are going to be really crucial intermediates in a week or so in the class. So this is just a preview of something that's going to be very important as the class goes on. So the lesson here is, the lesson that you're going to need later on is we're learning that alpha carbons in aldehydes and ketones, or alpha carbons next to carbonyls, are acidic. That's something we didn't learn last term. Alpha carbons next to aldehydes and ketones are acidic. Last term we saw a lot of reactions where we did an E2 or an E1.
Wait,
where the
alpha carbons next to what?
next to a carbonyl, I should say.
Oh, I thought it was the alpha hydrogens.
Well, those are two ways of saying the same thing. Yeah. When you say that alpha carbon is acidic, what you mean is that its hydrogen is acidic. So the alpha carbon in a carbonyl containing compound is acidic, or you could say the alpha hydrogen is acidic. Last term, we saw a bunch of E2 and E1 reactions where the base took a beta hydrogen. But now we're seeing a case where the base takes an alpha hydrogen. Well, how do you know which one it's going to take? Well, last term we weren't talking about E2, we weren't talking about the base attacking aldehydes and ketones. That's why it was attacking the beta carbon. But when you have an aldehyde or a ketone, the base is going to attack the alpha carbon. Okay, so the lesson here is simply that the alpha carbon in aldehydes and ketones is acidic. That's something you're going to need as the course goes on.
It says some supplemental chapter 17. Where would that be? These?
Can I see where it says that?
Here, like supplemental chapter 17.
I think all he means is that this is a supplemental exercise. He still wants you to do exercise 4 in chapter 17.
Oh.
You just go back to exercise 4. He's just saying that this is less
Really?
important than the other suggested homework assignments. Notice, these are the suggested assignments, and these are the supplemental assignments, is all he's saying. So he's just saying these should be a higher priority than this over here.
All right.
But it's still just in the exercises.
How would you tell the difference between these? Using only mass spec. This is own and it's own. Okay, that's just wrong. So basically we're just going to look at the cleavages right now, because that's what's going to be different from. So here we need to know the cleavages, right?
Right.
And McLafferty, so whatever.
So what were your thoughts about this problem?
Well, the alpha cleavage
Mm-hmm.
would be,
So let's see, the question is, how can we tell the difference between these two compounds using mass spec? The question is, how would the mass spec for this compound
yeah.
be different from the mass spec
If we
for
do
this?
the alpha cleavage for both of those, they would be the same.
Would they? So what would the alpha cleavage be?
Here or here.
Ah, I didn't think about that.
Yeah.
That's a good point. So
Those
the
would
alpha
be-
cleavages would cleave these bonds, but this fragment is the same weight as this fragment, and this fragment is the same weight as this fragment. Good point. So the alpha cleavages won't help us. So what would help us?
McLafferty.
McLafferty rearrangements?
Yeah.
Okay, McLafferty.
So that would McLafferty steals the gamma hydrogen. Could you over? Could you go over?
Sure.
Please.
So that's right. The McLafferty rearrangement is when the carbonyl oxygen steals the gamma hydrogen. So here we've got alpha, beta, here's the gamma carbon. So here's the gamma hydrogen. Now, of course, we're supposing this is our parent ion here, so I should be supposing this is the radical cation. So here we have the radical cation, and this can go through a McLafferty rearrangement. It's good to actually draw the mechanism for the McLafferty rearrangement.
What steals what exactly?
In the McLafferty rearrangement, the carbonyl oxygen steals the gamma hydrogen. That just has to be memorized. I think this is the first time we needed to focus on a gamma carbon, but it's right after the beta carbon. In our McLafferty rearrangement, the carbonyl oxygen steals the gamma hydrogen. Oh, but maybe I should show that happening. Let's not use a lone pair. Let's use the pi bond. Is that what they did in the book? Absolutely. So the oxygen uses its pi bond to steal gamma hydrogen. Oh, my arrows were all wrong. Let's try again. That frees up these electrons to move over here. And that frees up these electrons to move over here. Now, if we pay close attention to the arrows, we should be able to draw what the fragments are from this. So let's take our time and draw the correct fragments from that. You got a problem with your arrows. We don't want to have that. So we don't want to move these electrons, we want to move these electrons. So I think you have an arrow that looks like this. I think you have an arrow that looks like this. But instead, we want the arrows to be coming after each other. We want the hydrogen's electrons are coming in towards the beta carbon, and then the beta carbon's losing its electrons and then moving over here towards the carbonyl carbon.
Oh, okay.